All right. Good, everyone. Let's do our final lesson of the week 8 lockdown work. And in fact, this is going to be our final lesson for chemistry. This is the last bit of content I have to teach you. Kind of sad and unfortunate that I'm not able to celebrate our last lesson of content together, but we can just celebrate later. And it also means that the good news is that basically we are in week 8 and we finished content, so that means basically you have week 9 and week 10 to work on your essays or start revising for your exams. Hopefully by this point you have an idea of um, which exam material you feel better on. You're encouraged to do both, but some of you guys might want to drop one of them, just so you can kind of focus on one and not spread yourself so thin, and that's fine. So, like I said, those two exams will be the organic chemistry or this thermochemistry material that we are finishing today. So, to wrap us all up, I now need to talk about entropy. So, we're going to be exploring entropy and processing how it affects whether or not a reaction is going to be spontaneous. One of the things I've realized in my past teaching is that people don't know what the word spontaneous means, or at least in the chemistry context. So basically, it's just a chemical reaction that will occur on its own. You don't need to provide any energy to get it started, so I don't need to put UV light on it. It's just gonna happen like that. So that's what we're thinking about with spontaneous. Now, some of these reactions are spontaneous and some of these reactions are non-spontaneous. If they're non-spontaneous, I need to provide energy for the reaction to occur, often in the form of heat or light. So, we are looking at number 8, explaining the properties associated with entropy. This is actually grouped in with enthalpy because you'll see that these two things tie together to decide the spontaneity of a reaction. So, cool. I forgot that I did give you guys a definition for it. All right, so when we're talking about spontaneous reactions, many of them are exothermic. But I want to add that that's not the only deciding factor. You can have endothermic reactions that are spontaneous as well. And so this is where the entropy is going to come in. So, for example, if I took ammonium nitrate and I dissolved it into water, I don't need to add anything to get that dissolving to occur. But when I touch that solution, I will notice that it feels cold. So that's telling me endothermic. The other example is baking soda and vinegar. If I mix those two things together, you should see a drop in the temperature. But we know that that happens spontaneously without any kind of need to get it going. So that is where the entropy is now going to come into play. So let's first explain what entropy is, because this is going to be a brand new word for you guys. It's just measuring the amount of disorder of energy or the disorder of matter. So it's basically just a measurement of disorder. Now we can tie in the second law of thermodynamics. So we looked at the first law in the previous lesson, and now in this one we're looking at the second law. So the second law is any spontaneous reaction, the entropy of the universe will increase. So basically, the universe wants to go in increasing disorder. It's not going to spontaneously go backwards and create more order. It wants to create disorder. Some examples to think about is like if I had a container filled with gas and I had a valve, and let's say I open the valve, it will move to fill the other side of the container. Now, you know this as going down the concentration gradient, but the reason why it's doing that is because there's more disorder in this reaction over here because now my particles are more spread out, and they're moving around, whereas in this case, we had them all kind of neatly packed in one side of the container and the other side was completely clear. So basically what will not happen is, let's say I have two containers, both with the same amount of gas particles, and I have a valve, and then I open up the valve. I'm not going to see all my gas particles move to one side and basically increase the concentration in one side and decrease the concentration in the other side. That's not going to happen because that's increasing the order. It's basically like tidying up. If I opened up that valve, I'm just going to continue having the same thing, which is just the gas particles will move around and they're going to be equally distributed because that is the most disorder you can get in that system. So that's what we're looking at when it comes to that. Here's a little joke that I hope you guys will appreciate. If you're ever nagged to clean your room, you can blame entropy, because that's the natural state of things. Things are going to get increasingly disordered. So that's what you'd expect. Cool. So there's several different factors that affect entropy, and when we're thinking about the randomness of matter and the energy and disorder, the first thing is the state. So as I'm changing from a solid to a liquid to a gas state, there's an increase in entropy because now there's an increase in disorder. When something's in the solid state, it's nicely packed together. There are either bonds or forces that are holding that component together to make it in that nice ordered structure. As I increase, then those gas particles or those molecules are now in the gas state and able to move around in a crazy, unpredictable manner, and that's very disordered. So, physical state is an easy way for me to tell whether or not the direction of disorder and how it's going. Cool. Another factor is volume. Now, this is only specific to gases, and basically, if I provide more space, there's more space to move around, and then that increases the possible locations that my particles are being, and so thus more disorder. So, very similar to the one that we were talking about with the valve and things moving down concentration gradient. Cool. Another factor would be temperature. So, the higher my temperature, the more disorder I have, and the reason why is because when you increase the temperature, you are then able to give more energy to the particles. The particles are able to move faster, there's more kinetic energy, and that's, with everything moving faster, there's a lot more disorder. So think about, people walking in a room and try not to bump into each other versus people running in a room and try not to bump into each other. And then the last thing to kind of think about as factors of disorder is the number of particles. The more particles I have, the more entropy that is then present in that system. Another one is the complexity of my molecules. So basically, the more complex my molecule, the more entropy it has compared to that simple molecule. And that's just because there's more possible patterns and things like that. Cool. So, now let's talk about the entropy changes. You'll never, ever need to do this calculation. It's just theoretical information to help you justify your answers. So this is going to be a common question that you're going to get as a tag-on to the enthalpy or Hess's law calculations that you'll then need to use. Because they'll often just, talk about the reaction, and then they'll say, would this reaction be spontaneous or not? So first thing we're going to be thinking about is the entropy of the system. So you basically look at the disorder that's in the products and you subtract away the disorder that you have in the reactants. Very similar to what you were doing with the enthalpy Hess's law calculations that you're doing in the last lesson. If I have a positive number and basically my products have more disorder than my reactants, then I am increasing the disorder of that system. So net change is more disorder. If I have a negative number and my products actually are more ordered than my reactants, then that is going to decrease the entropy and I'm going to have more order. Basically, what we're trying to do is the reaction is going to try to proceed in the way that you're going to maximize the disorder. And the units for this is going to be joules per mole per degree Celsius. This doesn't, though, give us a lot of information until we look at it in the context with the enthalpy. So, but do keep in mind that a common question they might ask you is they might give you an equation and they'll ask you which direction will it proceed based off the entropy, and you can tell by looking at the information such as complexity, number of particles, temperature, volume, and physical state. Most likely you're going to be using physical state, number of particles, and complexity, because that stuff you can see in an equation. Cool. So now let's talk about Gibbs free energy. So Gibbs free energy is factoring both the enthalpy, so the energy change in the system, and the disorder that that system creates. And that's going to then decide, when you do that comparison, whether or not you have a spontaneous or non-spontaneous reaction. So even though we are trying to maximize our disorder and get to a large entropy value, that entropy value is also in reference to other factors such as how much energy is going to be required or released for that reaction. The other thing that's important to remember is the temperature. So you have to remember at different temperatures, some reactions will occur spontaneously and some reactions will not occur spontaneously. So do kind of keep that in mind. So for example, we know that water will go from a liquid to a gas at 100 degrees Celsius. Now, if I have it below 100 degrees Celsius, this reaction is a non-spontaneous reaction. However, if it's over 100 degrees Celsius, then it will occur spontaneously. So do keep in mind that the temperature is a very important factor. This here is a nice little summary list of what you're looking at in relation to the enthalpy versus the entropy, and basically at what temperatures will it be spontaneous or non-spontaneous. I'll go over to the OneNote now so I can kind of talk you through this. It's really kind of just generic math principles. Again, you will never be expected to do this as a calculation, but having some basic understanding of how numbers work will help you kind of make sure that you're doing things right. So let me move over to that guy. All right. So some things to think about when we're looking at this equation. I'll start with the ones that say temperature all, and just think about kind of how numbers work. So all temperatures, if my enthalpy is positive, so delta H equals a positive number, and then my entropy is a negative number, I'm subtracting a negative number. So in reality, if I'm subtracting a negative number, that is a positive number. So if I'm doing positive plus a positive, I will always get a positive number. So since that's always going to be a positive number, it's always going to be a non-spontaneous reaction. Doesn't matter how big or small those numbers are, you add two positive numbers together, they're going to still have a net result of a positive answer. So what that basically means is that if I have an endothermic reaction and I am, in this case, remember that if the entropy is negative, you have less disorder, so it's being more organized. So less disorder, more organized. So if I have both of those conditions, that's going to basically be a non-spontaneous reaction. It's going to be really hard for that reaction to go ahead. Right, in the other all example, you have a negative enthalpy and a positive entropy. So again, think about how numbers work. Delta H in this case is a negative number, and I'm subtracting away a positive number. So in this case, I'm basically going to have two negative numbers together. And since I have two negative numbers being put together, I'm always going to get a negative number as my answer. So since I'm always getting a negative number as my answer, then that's going to be spontaneous. So this one has to be spontaneous. So basically, again, if we're breaking this down, a negative number means I have an exothermic reaction, and a positive entropy value means that I'm increasing disorder. So both of those are, things that are going to, especially that increasing disorder, it's going to really encourage that forward reaction. All right, the other components here really depend on the temperature. So if the temperature is high or low. So again, let's do some math to think about this. If I have a positive enthalpy and a positive entropy, so delta H is a positive, let me erase that. Oh, I should be writing Gibbs. I'm so used to writing H's. We're talking about Gibbs. All right, so with that G value, so if I have a positive number and I'm subtracting away another positive number, basically these are competing values, and the bigger of the two numbers is going to result in my net reaction. So I'm basically asking, is delta H or T delta S bigger? Is the question. So if my delta H is bigger than my temperature of my my T delta S. So basically my temperature is a small number because that's going to result in a small combination of the entropy. So I'd be doing a positive number subtracted by a small number, and so the net so we're going to net a positive number for the answer. So since I have netted a positive answer for that, that's going to then be a non-spontaneous. I'm just double checking that I'm right. Yeah, low, non-spontaneous. If, however, let me get another green color, so that way these pair together. If, however, I have my delta H is smaller than my entropy, and this is going to happen if my temperature is high, then my net answer, we're going to have positive subtracted by a positive. This positive number is larger than that one, so that's going to actually result in a negative value. So my net number is negative. And that's going to be spontaneous. The other way to kind of think about it, if you're kind of struggling with this concept of big number, small number, is that just assign values of numbers to it. So you can assign that this is 10, or sorry, this is 100 and that's 10. And if you do 100 minus 10, well, then you have 90. Whereas if you flip these numbers around and this is 10 and that's 100, well, if you have 10 minus 100, you have negative 90. So you can just like assign some random numbers to help you visualize what's going on and what your net answer is and what's going to be spontaneous and non-spontaneous. Basically, what this is trying to tell you is that an endothermic reaction can be spontaneous if you have it at the right temperature. Cool. Which is why stuff like the, what was I going to say? It's like when we're dealing with the baking soda and vinegar, you mix them together, and at room temperature, there is actually enough energy for that to be a spontaneous reaction. If I lowered the temperature and there wasn't enough there, then it would be a non-spontaneous reaction. So keep that in mind. It might be something worth playing with. I don't know what temperature you need it to be at for it to be non-spontaneous anymore. All right, I'm just trying to find another color that would work. Might do black and gray. All right, so the other example is we have a negative enthalpy and a negative entropy. So in that negative entropy, we are creating more order. So even though this reaction is exothermic, it's going to create more order in the process. And again, like I said, it boils down to the temperature. Is it high or is it low? So let's, like I said, do some math and see it out. With my Gibbs free energy, if I have a negative number and I'm subtracting away another negative number, and I'm trying to see how this is netting out. So if I'm doing subtract and subtract, just double checking I had the right thing. So this is actually being added. So I'm saying I'm adding a negative number with a positive number. And basically, whichever is going to be the larger of the two numbers is going to decide the sign of the signal. Sign of the signal? Sign of the answer. So let's look at that again. So if my delta H value is greater than my T delta S value, so I have this number here is bigger than that number there. Let's plug in some numbers just to think about it. So let's say this is 100 and that's 10. So I have negative 100 minus negative 10. My net result, add them together, is negative 90. So in that case, if I have a low temp then I should have a spontaneous reaction, which I do because that's a negative number. So hopefully that's sitting okay with you. All right, and that's why I like to plug in numbers to say as an example. If my delta H number is smaller than my enthalpy multiplication, and this is because I have a high temp, then let's say this is only 10, and that's 100. So I have negative 10 minus negative 100, so that turns into a plus, and my net result is a positive 90, for example. Well, then this combination, exothermic reaction, increasing disorder, but at a high temperature, that would be non-spontaneous. Let me just double check that I have that the right way around. Yeah, I do. Cool. So that's what you're looking at. That's what you have to be kind of mindful of. There's going to be certain kind of things that you need to kind of factor in temperature with, but other things that, regardless of what the temperature is, you're always going to get a positive or negative number. So just kind of think about it in a mathematical sense. If you're not sure what to do, just assign numbers to it and then do the basic kind of calculations. When you assign numbers to it, you're just assigning the blank number without any signs to it, and then you're using the signs when you're actually plugging it into the equation. And hopefully that'll help you kind of decide which reaction you are, or sorry, whether or not the reaction is spontaneous. And that's Gibbs free energy. So depends on the enthalpy. It depends on the disorder that it's creating. All right. Kapai, that's everything for today's lesson. So we were exploring entropy and also how does that affect the spontaneity of the reaction. You'll need to use Gibbs free energy for that. Do number 18 when it comes to follow-up work. There is also a CPR quiz for this on Hess's Law, so you guys can practice this. All this stuff is on Google Classroom. So congratulations, you have now learned everything in high school chemistry.